Okay, so it looks like about everybody's in here, so let's get started soon. So today we're going to be having Allison. She's going to be presenting to us. She's going to be presenting about NLP, natural language processing. She has a lot of good information set up for us, so let's hear what she has for us today.
Thanks, Josh. All right, so first I'm going to go ahead and send you guys a link to a Google Drive. I have a couple of files and then also a collab in there if you want to follow along with me, or if you just want to have it for reference. So I'm going to put that link in the chat for you guys. Okay, so it's in the Zoom chat, and then I'm also going to put it in the chat on Discord real quick too, just in case. Right, and if you can't access it, let me know and I'll try to fix permissions, but I think it should be good. Okay, so we're going to talk about natural language processing today for a little bit, and then the last 15 minutes of the class we're going to leave open for Q&A. So that'll be a great time to ask any of your questions. If you have anything in the meantime though, you can feel free to pop it in the chat and I'll take a look at it as we go as well. But yeah, thanks for joining. So this class is Intro to Natural Language Processing. And so what is natural language processing? Well, it's a field of study that combines data science and machine learning and human language. So it's a very interdisciplinary field. It's also pretty up and coming. There are a lot of areas of natural language processing right now that are being studied very heavily, which makes it really exciting. And some example applications of NLP are stopping spam emails, identifying fake news, analyzing sentiment, chatbots, translation, spell check, you name it. There's a lot of different applications for NLP. And this is also a very useful course because several of our challenges you could make good use out of learning about natural language processing. Yeah, for example, I think the one that is building a recommendation engine for TAMU Datathon, that uses quite a bit of text analysis and going through all of our applicant data. So I'm hoping to also kind of cover some ways that could really be helpful to you if that's a challenge that you're taking, or just if you want more info on it. But as far as what we're going to cover in the course today, I've broken it up into about 3 sections. So the first is text preprocessing, which is really examining how you can take base text and then turn it into a form that really kind of enriches your data set, so keeping things that are useful. And then the next section is going to be talking about feature engineering, which is the process of taking text and turning it into numeric form. And then lastly, we're going to look at some classification and sentiment analysis. The Python packages we're going to use, especially for the text preprocessing part, is bulk NLTK, which I believe stands for Natural Language Toolkit. But it's a very useful Python package. There are actually several out there that are very good. This is just the one I've chosen to base my collab off of. And we're also going to use scikit-learn once we start getting into the modeling and feature engineering portions. So I've already run most of this, so you can just kind of see the data that's been saved. But if you're following along, you can go ahead and start running all of these. And so we're going to start with text preprocessing. So what is text preprocessing? Well, it's the steps to clean and prepare human language text. And the goal of doing this is that sometimes well, actually a lot of the time, you're given text that is extremely messy, and you're needing to go through it in order to take what's most important out of it so that you can use it to model. So you're kind of getting rid of all the fluff, you're consolidating things, you're really just keeping what you need. And this can help improve model performance. And there are a lot of different steps to text preprocessing, and you're not necessarily supposed to use all of them at once. It kind of depends on your text that you're based off of. But these are all just good techniques that I wanted to mention. That way you could just kind of have them in the back of your mind and know about them. And so these are tokenization, stop words, alphanumerics, stimming, and limitization, which go together. Also lowercasing, part of speech, named entity recognition. And then I also wanted to throw in there a little bit about how to do a word cloud visualization, which isn't necessarily a text preprocessing step, but it just kind of helps give you an overview of what you're looking at. All right, so the first one of these is tokenization. And so this is the process of splitting text into smaller pieces called tokens. And there are several different types of tokenization. In this lesson, we're mostly going to use word tokenize and sent tokenize. Word tokenize essentially takes string and it splits it on a space, so it'll get you different words. Sentences will split it on punctuation, so like the end of a sentence. Regex, if you wanted to, or if you're familiar with regex, you're able to pass in patterns, and that's kind of how you can go about and split into your tokens. And there's also a special tweet tokenize that is really, it's good for any type of tweet data as well as text data, because you can do some special things with emojis, as well as hashtags. It can know to group certain things together with the hashtag that may not be parsed that way in a different type of tokenizer. But like I mentioned, for this particular lesson, we're mostly going to be using word and sent tokenize. And these can come from the NLTK package, so you can see this in the code right here. And I've gone ahead and I've made a variable text with some random text in there. And as far as tokenizing things, it's really as simple as just calling the function on the string for both the word tokenize and the sent tokenize. And so if you do this and run it, you can see that the word tokens did split it on space. Something to note though here is that it counts punctuation marks as a word token, which is going to be something we're going to want to filter out later. So just kind of keep that in mind. And then sentence tokens are exactly what you'd expect them to be. And next we're going to look at stop words. This is the next thing we want to consider. And there are a lot of really common words. And so, for example, A is and the are ones that I pointed out, but they don't carry any important meaning, and so we often remove them. And this is a concept we're going to come back to later with some of our feature engineering models. But words that are used really frequently that aren't important should really be taken out because they're taking up a lot of space and they're not giving you any predictive value. And so we want to remove these words. And there's a package in NLTK that has a base English stop word. So some of the ones I mentioned earlier would be included in this. And so after you tokenize into words, you can do some list comprehension. And this says for every word in your tokens, you're going to keep it as long as it's not a stop word, and you'll get rid of it if it is a stop word. There's also a way that you can customize these stop words. And an example of when this would be really useful, so say that you are looking at some airplane data and the word plane comes up over and over again. It may be super frequent in all the text you're looking at, but it's probably not going to be very useful modeling if it's in every single sentence. So that might be a case where you would want to customize your stop words for your particular text. And you can do this because the stop words are a list, and so you can just append different words that you want to include in your stop words. And then when you iterate on it, it'll take those words out. And so if you look at this output, for example, you can see the original output is just all the tokens, and we were just doing word tokenize on this sentence. And then when I took out stop tokens, it took out the words are, in, and a, which would be really common English words. Those were included in the base English stop word list. And then in this example, I just kind of randomly took we and I put it into the stop words just to demonstrate. And so we was taken out once I added it into my stop word list. So that's how those work. And now we're going to look at some alphanumerics. So there's a couple of different ways you can filter. You can use is alpha to indicate whether or not you are looking at a character, is digit to see if you're looking at a numeric token, or is alnum, which would be either characters or numerics. And so if you wanted to filter this as well, the first several steps are very similar. You just go through and you tokenize, but you can do some list comprehension on these 3 different functions and include the type of words you want. So if we look at the output, you can see how things differ a little bit. The first one has every single token, and the next one is character tokens. So anything with a number at all is removed, as well as the punctuation. So you're left with just words. Numeric has to be entirely numeric, so you're only left with a 25. And then alphanumeric, you have everything but the punctuation. So that's how that one works. And then the next text preprocessing step we're going to talk about is lowercasing. And this is actually really useful, especially when you're looking at different kinds of forms. I think the example that comes to mind most to me is with addresses and states. There are so many different ways that you can do your state abbreviation when it really all refers to the same thing. And so a really easy thing to do when you're preprocessing text is just to go ahead and make everything lowercase so that it refers to the same word. And that's really easy to do as well in Python. after you tokenize your strings, you can do list comprehension where you're going through and you're lowering every single item in there. And you can see this example, yeah, everything was completely lowercase after doing this. The next one I want to talk about is stimming. And stimming and limitization, which is the next one, are very similar. So we're going to kind of compare and contrast them a little bit. But stimming is the process of reducing words to their root form. And it does this by just cutting off the ends of words. And so the whole goal of this is a lot of times you have words that are conjugated slightly differently, but they mean the exact same thing. And so if we think a couple of steps forward and we're trying to model based off of our text, we don't want different features for different conjugations of the word. We want to go ahead and reduce that dimensionality and say that a word has the same meaning regardless of its conjugation. And so that's what stimming really tries to do, and it does this by just chopping off the endings and trying to reduce it to a root form. But because it just chops off endings, it can put them in kind of weird places. It doesn't always actually make a valid word. And I'll show you an example of this. So with universe and university, it just kind of takes that ending off. And so they both end up being this spelling of universe, which isn't actually a real word. And in here, I picked this example on purpose because it shows kind of a pitfall of stimming. These two words mean different things, but they would have the same stem, which actually, yeah, that's not a great thing in this case. You want them to be different. And so that's just something you kind of have to be on the lookout for with stimming. You can do this with this function called Porter-Stemmer in NLTK. And so what you'll do is after you tokenize all of your text, you'll call the Porter-Stemmer function, and you can stem each of your words in tokens. And so in this example, I picked this string because if you're thinking about what you wanted to be similar, we would want test and tests to be the same stem because they refer to the same word. You would want cacti and cactus to be the same as well, but you wouldn't want universe and university to be the same. And when we put it through the stemmer, what ends up happening is that test and tests end up being the same because what stimming does is just cuts off that last letter or the last couple. So in this case, tests could reduce down to test. But cacti and cactus, even though that we would want them to be the same, don't, because cactus can never become a cacti in stimming because there's no I in it. So like it can't cut off anything and become the same. And in this example, we didn't want universe and university to be the same, but they were able to be. And so knowing that these are some issues that can come up with stimming, we're going to now look at limitization, which addresses some of these things. So limitization has the exact same goal. It wants to reduce things to their root forms, but what it does, instead of just chopping off endings, it actually has a predefined dictionary of lemmas. So people have gone through and actually kind of figured out what groupings of words go together. And this takes a little bit longer to run, especially large scale, than stimming does because you're having to refer back to the dictionary every time, but it's more accurate. And the lemma is always a valid word. You're never going to have a word that's cut off to something that isn't actually a word, like we saw with our university and universe example. And as far as you run it, it looks very similar, only you're using the WordNet limitizer instead of the Porter-Stemmer. And so with this exact same sample string, remember we're expecting the first pair to be the same, the second pair to be the same, and the third to be different. You can see that when we limitize, again, the first pair came out to be the same, but now you have cacti and cactus that are the exact same, which you wouldn't have ever seen in stimming because they don't have the same ending. But here, because it's looking it up in a dictionary, it actually knows to group them together. And also, it knows at the end, universe and university, and wants to keep them separate. And so limitizing here does better than stimming. And I think there's a note in the chat, so I'm going to open it up and see. So Sam asked, why do they not just both become cact? And I assume you're referring to the stimming example with cacti and cactus. Yeah. So I don't exactly know how the stemmer decides where to cut it, but yeah, so I'm sorry, I don't exactly know where it would cut. But it would never be an actual word either, which is also the problem with stimming. So even if they did both reduce down to cact, it's not a real word. And so that's also something that limitization corrects, because so it doesn't just put them to be the same word, it also makes them a real word. Does that make sense? So I didn't quite answer your question as to why they don't become cact, but here they become the same and they're an actual word. Yeah. Thanks for asking. Okay, so that was stimming and limitization. And then our next section is part of speech tagging. So there's actually functions in Python where you can put in text and you can figure out what kind of speech it is, just based on the definition of the word. And you can use this pause tag and NLTK to do this. And so after you tokenize your text, which is the theme of every single one of these examples, that's the first step, then you can pass it into this pause tag function, and it'll have identified each of your words as to what kind of text it is, which is kind of neat. And then if you look at named entity recognition, it takes it one step further. So here it just does, well, actually it's pretty descriptive, but you have different types of nouns and verbs and adjectives, those kind of things. But once you get to named entity recognition, it's taking nouns and it's seeing whether or not it's actually a named entity. And so this would be like a person, a location, an organization, all of those like officially named things is what you're looking for. And you can do this by wrapping it in the anyChunk function after you do your pause tag function. So in this example, my text is the Eiffel Tower is in Paris. And so we're word tokenizing, then we're doing the part of speech, then we're doing the named entity chunking. This code right here at the bottom, the output of the anyChunk is a little weird. So it's just kind of formats it in a way that we want to look at it. But something that I think shows like the power of this function here is we word tokenized it. So you know that in the function, each of these individual words is now a thing. But because of the named entity, it actually knows that Eiffel and Tower go together. So even though they were separate words, it can pair them together to know that it's a named entity. So it shows it's able to recognize that. And then it also pulls out Paris too. So it's kind of just an expansion on the part of speech tagging. And I think there's another comment. So I'm gonna look in there. So it's more like using stimming first and then limitization to correct the mistake of stimming. Yeah, that's pretty much, especially the way I portrayed it. There are advantages to stimming, and I purposely picked out examples where I knew it didn't work. So it's not like it doesn't work all the time. It does a fairly good job. And if you're running a lot of data, like I mentioned, limitization, you do have to look it up in a dictionary, and so that can become kind of computationally expensive. But if you're just doing something like I'm doing for the purpose of this class, you would want to use limitization because you're more likely to have it correct. But yes. All right, and then so for the last part of this text preprocessing section, we're going to look at word clouds. I just think this is a neat visualization. In general, I think visualizations really help with data science because it just kind of gives you a grasp of what you're looking at and how to go forward. But a word cloud, if you haven't seen one before, what it does is it takes all of your words in the string and it portrays them in a way that places emphasis on words that are most frequent. And you can do this. There's a library called Word Cloud, and it actually has built-in stop words as well. So you can use those. And I put in the old subway phrase here. And then what you do is you instantiate this word cloud function. There's a lot of different ways that you can customize it to. You can change the background color. But I just set it like this. And then when you show it, you can see that because of the stop words, it got rid of the word any. So any is not in here anymore. And it goes in the order of how often it was seen. And each time you generate a word cloud, it looks slightly differently to you. So you can play with it a little, but the same principle is there. And this just kind of helps you get a glimpse of what you're looking at. So if y'all wanted to do any practice with text preprocessing, I left a practice problem in here for you. It goes off of one text file, and taking that sample text, it goes through each of the different steps that we talked about. And there's kind of like fill in the blanks. So if you just wanted to practice later on, you can, and just get a refresher as to what we talked about today. That was that whole first section. And then we can go ahead and move on to this next part, which is really important. This is really where you start going from looking at text to making something out of it. So feature engineering is all about transforming the textual data into numerical data. And this is because you have to use numbers when you're doing machine learning. And so you have to really think about this. It becomes a pretty big challenge because you have this text data and just like thinking about how to transform it into numbers that are meaningful it's a really complex task. And so there's a couple of different things that we're going to learn about. And the first is just some basic features. We'll talk about those in just a second. And then the last three are some more advanced models or more advanced methods that have been done to do this, to transform data into numbers. So first, we're going to look at basic features. And so some examples of these are counting the numbers of characters, words, or sentences, or averaging the lengths of those, or even finding the amount of capital or punctuation marks. And these are actually really useful in different cases. So for example, text readability. I was reading about this field of, especially in law, when lawyers are looking at different type of documents and they're trying to figure out if people would understand them, or in schools as well, if you're creating reading content for kids and you're wondering what level they would have to be to understand it. Something that could really be useful there is taking into account the number of characters or your average length, because a text that is pretty difficult will probably have longer words, longer paragraphs, and so you can use some of these basic features in order to assess text readability. You can also use this for sentiment analysis too, especially more on the capitals and punctuation marks aspect of it. If someone has a very strong opinion about something, you may see that they type in more capital letters and more punctuation marks. And so calculating some of these basic text features could be influential in some of these cases like we talked about. And so in order to do this, I created an example right here. So it's a list of different strings, and I went ahead and I word tokenized all of them. And then you can just calculate the length pretty simply and less comprehension just by taking the length of everything in your tokens. And you can see that here. And then the average length is pretty similar to that as well. Now you're adding all of them and then dividing by how many there are. And then so you can get the average lengths here. And so, yeah, these are methods that you kind of take a whole list of something and you just find one number. So that's what these basic metrics are, but they can come in useful. Okay, and so now the next three, we're really going to think about how can we store more of the important information about the text, because before we didn't store any meaning about what the text said at all. We were just looking at kind of lengths and counts. And now with these next three, we're thinking about how can we actually remember what the words mean and incorporate that into our models. And so the first of these is the bag of words method. And before we get into bag of words, I wanted to mention on one-hot encoding just a little bit in case y'all aren't familiar. But this is a method that's used not just with NLP stuff, it's used kind of all across machine learning. But what it does is it takes a categorical column and it turns it into numerical data. And so for each of the items or each of the categories, it becomes a column. And then you have binary values. So 1 if it was in that row and 0 if not. So here's an example of how you could do it with the days of the week. But this is a concept that we're going to apply in this bag of words method. So what bag of words does is it looks at your text and then it's going to be able to, using the tokens, so your tokens then become your columns. And then you can do kind of one-hot encoding there as well. So you can count, so it's not just a binary 1, 0 like it was with one-hot encoding, it's also a count here. So you see the frequency of how often that word was in the row. And so this is what a bag of words model looks like. And something to think about here too, in this example, there were only 4 words in each row. So you don't have super high dimensionality, but imagine you're building a vocabulary of a lot of different rows with way more words than that. You're going to gain a lot of columns really, really quickly. And so that's something you want to really keep in mind, because you do want to keep like the important information. You want to remember the meaning behind words, but not at the expense that your table just gets super huge, because that's not great either. So that's the curse of dimensionality. So you have to find this balance between having too few features and too many features. Some of the steps that we talked about earlier, preprocessing, can help reduce this dimensionality, especially if you think about removing stop words, so taking away the words you don't need, or limitizing, so kind of condensing things. That's where those steps really start to come in handy here, because you can use that with your bag of words models. And so how do you implement bag of words in Python? Well, you take the count vectorizer function in sklearn. It's one way to do it. And it has some built-in pre-processing steps, which are really nice. So you can lowercase or do your stop words, or even do a token pattern, which is more like regex on it as well. And there's some parameters you can play with, which are going to lead us into the next model a little bit more. But there's a max features parameter. So if you didn't want all of the words to become columns, you could set max features. And so after it had seen a certain number of words, it would stop creating new columns. So that's a way that you can help fight dimensionality. Then you have max df and min df. And so df here stands for document frequency. And so that is how common a word is across a whole lot of different texts. And so you can hard code a percentage for max df and min df. And so if a word is more common than your max df, then you don't want to include it. So that's almost think about stop words in that way. If you see a word over and over again, you don't want it. So that's what that sets. Versus the min df too, if you have a word that is so infrequent, it probably also isn't very useful either if you like never see it. So those are two ways that you can kind of get those edge cases in there. And then the last is an n-gram range. And so an n-gram, I provided some pictures below, but bag of words, as we saw earlier, and as you can see in this first one, it automatically tokenizes by word. So you're just looking at one word columns. And this takes out any type of context because you have no idea how it's being used. A lot of times words on either side really affect the meaning. And you can see that here. So happy, not sad, and sad, not happy mean totally different things, but their bag of words would be the exact same. And so you don't include all of that meaning. And so an n-gram now groups different types of consecutive tokens, and that can help provide more context. And so in doing this, we just made it a bigram. So we're looking at two words and all the two-word pairs. And now you can see that this representation would be different. So it would actually show that the two sentences were different. And so that's another parameter that you can set as well. But again, with this, you wouldn't want to necessarily just set your n-gram parameter way too high. So for example, if you set it up to 10, you may, I mean, it would show different meaning, but how often would you actually have the same group of 10 words over and over again? So then your dimensionality is getting huge, but it's probably not that effective. So there's a balance with the n-gram parameter as well. So that was a lot, but now to get to actually coding it, you can import that count vectorizer function we talked about from sklearn. And after, yeah, so here I've loaded in the text. And then you can apply the count vectorizer function to that series of text. And in this case, I went ahead and I did n-gram range of 1 and 2. So it's going to be all one words and then the pairs of words. And I passed in stop words here too. So then what you do, so vect, fit, transform. This could actually be written as two different functions. You could write it, or you could write it as vect.fit text series and then vect.transform text series, or this combination approach. But the fit part, what that does is it comes up with your vocabulary. So back when we were looking in here, so your vocabulary is all the different words that are going to become your columns. So that's what fit does. Fit finds that vocabulary. And then transform matches it. So once it knows its vocabulary, it's then going to do the count and produce that matrix. So it's two separate steps, but you can also combine it in this one function. And once you do that, we convert it back to data frame. This output actually creates a sparse matrix. So that's why it looks a little weird in here. You have to reconvert it into a format that looks more familiar to you. But after you do all of that, you're left with this data frame where you can see what it looks like. So you've now fit the count vectorizer function and you've produced a bag of words. So then the next version of this, I mentioned with the bag of words, you had a couple of different parameters that could kind of get at this. But this Tf Idf model, what it tries to do is you want to pick words that, well, it's the balance between term frequency and then document frequency, which is like the max df, min df thing we were talking about. So you want to pick words that are like not common across every single document, not too infrequent. You want words that are like in your particular piece of text are common, that they'll stand out. They'll be different from everything else. So that's what this model tries to do, is it tries to find that balance of really making sure you have the important words for your particular piece of text. And so Tf Idf, it stands for term frequency inverse document frequency. And so term frequency is this first part. If you are looking at a particular like row of text, then term frequency is the number of times a word appears in that row. And so if you have a word that's really common, it's going to have a high term frequency value because it's there a high proportion of times. And then document frequency, on the other hand, is if you're looking at a whole data frame of text, it's counting the number of times a word is seen in like each row. So like how frequent is it across everything? And so we take inverse document frequency. So words that are common across all of things are going to have a low value there. And so this way you're kind of balancing. You want words that are common in your row, but lower across all the other rows so they stand out. And so what you do here is you have this function, which we talked about. So it's the term frequency and then inverse document frequency, which creates this weight, this value. And so when you do it, you're not going to have a count anymore like you did with the bag of words that just said you have this word one time or you have this word two times. You now have this score, this inverse or this Tf Idf score that you're looking at. And so with implementation, it looks very similar, only you're just using a different function name. So you're using the Tf Idf instead of the count vectorizer. You have the same pre-processing steps. You have the same parameters that you can tune as well that we talked about earlier. And when you run it, it looks similar. So the only difference really here in terms of output is that now you don't have a count, you have this Tf Idf score. Okay, and then the last one I want to touch on is word embeddings. So these are really popular nowadays. What it does is so with the bag of words and the Tf Idf, you are able to start kind of piecing together meaning from words different than those basic features we were pulling out earlier that just did counts. The last two, you actually started retaining some of the words. And now with word embeddings, what they're trying to do is like create a model that has similarity between words. So now you're trying to say, like, we don't just want to store words, we want to see how similar two words are and use this in our model and for our meaning. And so word embeddings are based off of neural network models, which I'm not going to get into neural nets too much other than a simple example here. But what they do is they go through a bunch of different iterations trying to pull out features and then assign a vector to each thing based on those different iterations. And so they don't, like the iterations don't always make sense. In this example, I made it so that you can kind of conceptually understand, but they're not like pulling out things quite this simply. But so say you had these four words, you had king, queen, prince, and princess. And the first thing we wanted to see was their royalty score. And so in this case, I gave them all a high royalty score because they're all royal terms. And maybe the next thing it wants to put in the vector is masculinity. And then so king and prince are masculine and queen and princess are not. And maybe the last feature is age, and it can do that. So this is kind of what a neural network model does, though like I said, it's not as like clearly defined as royalty, masculinity, age. But this is the concept, is that you find different things connecting those words and then you give them scores based on it. And so now if you were to look at these words, you can kind of see how similar they are across of these different attributes. So this is the basis of a word embedding. And so how can you implement them? Well, there's kind of two different types. There are pre-made word embeddings that you can do from libraries. And so we're going to look at this word2vec from Gensum. There's also another one that I know we're using, or that's in the like demo code for our challenge. So if you're looking in there, you can see that as well. But these are like pre-made neural networks that have already gone through and calculated similarities for you, and then you can just apply them. You can also train a neural network model on a text and then come up with your own. So you can do two different approaches. You can like use a pre-made one or train your own. But with this one, this is Gensum's word2vec function. There are a couple of different parameters you can tune. So size and workers both relate to how the neural network is formed. Window is a parameter that you can say how closely related you want two parameters to be. And then min count, if a word is really infrequent, you can like nix that from the model. So it's kind of similar to some of the other ones we've seen before. But for this example, what I do is I import the Alice in Wonderland text, and then I do a little bit of pre-processing. So I lowercase everything, and then I only take the characters. And then now for the new part, so you would put it through this word2vec, all of your tokens, and I set the parameters. And then once you have made this model, you can compute some different things. You can find the similarity between two words. So here I did Alice and her. If you look at the output, they're pretty similar, which means that those two words are used in similar contexts, which you'd kind of expect, that you could use Alice and her interchangeably. And then the other thing that you can do with this is you can find the most similar words to your input word. So if you put in read, you can see some of the different ones that are output and then their relative scores to it. So that is an overview of word2vec and word embeddings. And like with the first section, I put a set of practice problems together for you. So if you wanted to go through and look, this one's with Harry Potter, you can do so and you can practice some of these different techniques. And I think I have a question in the chat. Let me go through. Is this mainly used to find synonyms and things like search engine queries? Yeah, that would be a really great application, which is why I know word embeddings would be a really helpful tool, especially for this recommendation engine challenge, because if you can go and look at some of your text and then see how similar it would be to a certain class, that's a really good way to then model. You can do classification pretty easily off of a word vector. So yeah, synonyms would be a really good example of that, recommendation engines. Yeah, that's exactly the point. All right, and so now that we have talked a little bit about text preprocessing and feature engineering, we can get into some classification. And so the purpose of talking about classification here is I really wanted to cover a little bit of sentiment analysis. And so this is classification specifically on trying to figure out a person's opinion within a piece of text. And there's a couple of different approaches to this. So there's a rule-based approach where each word has been assigned a certain positive connotation or negative connotation, and you would go through a sentence and you could actually like count up the negatives and positives. And then if your sum ended up being negative, you would say the whole sentence is negative, or vice versa, it could all be positive. So it's a rule-based approach, but you have to like know you have to know the defined connotation of each word and then add them up, and then you may not get them right because you don't take into account any kind of pairings of the words. You're just doing like adding individual words. That's one approach to doing sentiment analysis. And then the other is a more machine learning based approach, which we're going to talk about and do an example with. Okay, so if you aren't familiar with classification, I wanted to give just a quick rundown on what it is. So it's a form of supervised learning, which is when you build a predictive model based on data with known outcomes. So if you're given a data set and you're given the results, you can train a model, and that's what supervised learning is. And there's a couple key steps that I'm going to do in this modeling. So the first is train, test, split, which the purpose of this is you don't want to build the model on your entire training set because you could really overfit a model and you don't know if it's accurate in the real world. So train, test, split, what it does is it takes your data and it puts it into a portion that you're going to build the model off of, and then another that you're going to see how good your model did. And then after you do that, we fit the model, and then you can evaluate model accuracy. There's different types of scores you can do to do this. And then before I do the next step, I wanted to check the chat. Is there a way to detect sarcasm in any of these models? Ooh, okay. I like the way you're thinking. So sarcasm definitely would be more of a challenge, because we've seen kind of as we've gone through this whole lesson how you're building up on each other. So first we weren't even able to like understand the meaning of words when we did the basic feature engineering, and then we started putting in words together and then combining words to get similarities. So sarcasm is just it's a bigger challenge, right? It's another combination of that, of knowing that like it would kind of flip the similarity, right? Yeah, because like even though a word might mean something, like tone is a big portion of sarcasm. Yeah, so it's definitely, that's more of a challenge. And I think there is a way to do it, and really complex models, I think we get that. Yeah, it's very interesting to think about. So yes, back to where we were. So we just talked about supervised learning, and then classification is a part of supervised learning. So it's a task of predicting a specific class. So regression is the other big portion of supervised learning, which is when you're predicting a value, like a numeric value, and here you're predicting among a list of classes. And there are different types of it. If you're predicting between two classes, it's binary. If you're predicting between more than that, it's multi-class classification. And there are different approaches to solve those different types of classification. So the first example I wanted to go over is a logistic regression classifier. And we're doing this to end up doing sentiment analysis. That's the goal. Logistic regression, we're not going to get super in depth with the math here, just high level conceptually. What it does is it uses this logistic function, this like sinusoidal function, to determine a threshold for classifying data. So if you look at this, for example, you may have this class down here in this corner, which belongs to one of the classes, and up here in the right-hand corner, it's a different class. And so if you're looking at this function, you could say that there might be a threshold right smack in the middle, that if your x value was to the left, it would be classified as 0, versus if it's on the other side, it's a 1. So what it does is it fits this function so that you can find your threshold. So that's what logistic regression is all about. And to do so, I imported this IMDb data set, and then I took my x and y. So x would be all of your features that you're wanting to model with. So in this case, it's actually just one column. It's the review. It's a text review. And then the class is df.sentiment. So that's a, I believe it's 0, 1, if I'm not mistaken, as to positive and negative in this case. Yeah, so you have your x data frame is your reviews and your y as your sentiments. And then I imported a bunch of different things that we're going to need to build the model. So you have train test split, confusion matrix just kind of helps you look at the output afterwards, logistic regression model, and then count vectorizer, which is the bag of words, if you remember. And so the first step here is to split up all of your data into training and testing using the train test split function. And then we're going to fit the count vectorizer function on it to get the bag of words model. And you can customize your parameters here like we talked about earlier. Again, I just left it as the 1 and 2. And then afterwards, if you remember when I talked about the difference between vec.fit and vec.transform and the combination, this is where it really gets important. So with your X training, you want to fit the data to come up with your vocabulary to figure out what those columns are going to be that you're going to build the counts off of. And then you want to transform it. You want to actually count it. With the testing, on the other hand, you don't want to fit the data. And the reason for this is, say there are words in your testing data that aren't in the training data, then they won't be accounted for in the training of the model. And so you're not going to actually be able to come up with a count for them or prediction for them. So you base your vocabulary off of the vocabulary of the training and not of the testing. And so for this reason, you actually just transform the X test to be whatever the vocabulary of the training was. And so that's where the distinction between the two is really important. But anyways, once you have done that and you've created your bag of words model, you can then put it through the classifier for logistic regression. You can fit the model. And once you do that, then you can find the labels and then do your score. And so this model right here, all we did, we really didn't do much like text preprocessing at all. If you look at it, we just used stop words, and then we did the 1 and 2 n-grams. So not a whole lot of text preprocessing. But with it, we got a 0.86 classification score, which is really good for not doing too much. And there are a lot of different ways that we can mess with this, right? You can fix any of these different parameters. If you wanted to use the Tf Idf instead of a count vectorizer, you could. If you wanted to use a word embedding, you could as well. So there's a lot of different ways that you can play with classification and NLP in order to try to really maximize the model. So that was the first one. And then I'm going to briefly mention naive Bayes, just because it's another one that's pretty commonly used with logistic, or with, sorry, not with logistic regression, with classification and textual data. But this is based off of Bayes' theorem, which states that the probability of y given x is probability of x given y times probability of y over x. So it's based off of that theorem, this model is. And so what it does is it looks really similar in terms of implementation. You're just using this multinomial naive Bayes function instead of the logistic regression function. But other than that, it's the same thing. So you can pass it through this model as well and see how it does. And so I left y'all some practice problems too, a lot of the different combinations that we talked about. So for example, in the one that I had run originally, it was bag of words and the logistic regression. And then these practice problems, I did the inverse. So I gave you all the other different combinations. And so it could be kind of a challenge. You could go and see which of the combinations actually produce the best model. And that brings me to, I believe, the end of my lesson. So if y'all have any questions, I would be happy to answer anything right now.
Thanks, Allison, for that wonderful presentation. There was a lot of good information there. It's really dense and really insightful into natural language processing. So before we go on to Q&A, I have a quick feedback link. So this link has 3 questions. It literally takes 30 seconds to fill out. So if everyone could just click on that link real quick, just fill it out. It really would help us gain feedback and improve this lesson. So now, while you guys are doing that, if anyone has questions, you can put in the chat and then we'll redirect it to Allison and see if we can get some good answers. Okay, so one person asks why the vectorization part is done. So why is the vectorization part done?
Okay. There were a couple of different vectorizations we talked about. So there was the count vectorizer and the Tf Idf vectorizer. And so that's a part of feature engineering, which I mentioned. The whole goal is to take your text data and to turn it into a number, because you can't just put raw text into a machine learning model. It must have a number. And in particular, these 2 different types of vectors, what you're trying to do is not just count. Like with the basic features, we found different types of metrics, like the number of characters, the average words. With these more advanced vectors, what you're doing is actually trying to contain some of the meaning behind words. So instead of just getting a number, you're actually keeping the word in there, which will give some more meaning on a greater scale. So you're able to retain that in your model. And so that's the point of the vectorization, is to just get it into a numeric form, but then to also keep some of the meaning behind the individual words that are in the text. Does that answer your question?
Okay, so I think that pretty much I understood that question. So we'll move on to the next one. So Dustin asked, is Tf Idf per word or text?
So I believe Tf Idf is per word, because the parts of this, so it's term frequency and then document frequency. So term frequency is calculating the number of times a word is in a certain term. And so I like to think about it in terms of like a data frame. That's how I think about my textual data. So if you're looking at like a column that has lots of different rows of text, so term frequency would be looking at one specific row and seeing the number of times a word is in that row. Whereas the document frequency is looking at all the columns and counting looking at all the rows and counting how many rows that word is in. So with both cases, it's looking at the individual word for Tf Idf.
All right, there's another question from Saurav. He says, can you create your own custom word embeddings?
Yes, you can. And that's part of, you build a neural network on it to create a custom word embedding. And it does take a good bit of time. So depending on the type of project you're looking at, it does take time to build a neural net model. I know for our particular project, I don't know if you've looked at it at all, but the whole thing is based upon our TAMI Datathon course curriculum and challenges. And so based on people's queries for things that they're looking for in TAMI Datathon, you're supposed to predict what they should go to, what class would be good for them. And so you can, for this challenge, you could go and you could use a word embedding that was already pre-made, and there's nothing wrong with that at all. But I know we had talked about there are a couple different ways that you could make this even better. So for example, there's a collection of data science articles that if you were to go and you were to build a word embedding model off of just data science articles, you're more specific into that area of focus, and then your word embedding may actually perform better. So yes, there are times where you definitely can create your own custom word embeddings, and there are times where it would be really beneficial to do so.
Yeah, are there any more questions? If there are, please put them in the chat. Okay, so it seems like that's all the questions for today. Thank you for presenting, and thank you for coming to our talk. It was really nice and informative. We hope that you got a lot out of it. And thank you, Allison, for putting so much time into creating this class and making sure that we have all the tools necessary to be successful.
Of course,
wait,
thanks, Josh. Oh, wait,
oh,
another question.
There's one last question. How do we calculate similarity between several sentences and 2 words?
All right, so I assume you're talking more about word embeddings here with similarity. And so that goes through, if you imagine in this example, it created this vector based on different categories, kind of. And so it's almost like calculating a distance between the 2 vectors is what it ends up being similar to. So if you think when you build this model, it's going to be way more complex. There's going to be a lot more features in your vector, but it would be kind of just calculating the distance between the 2 vectors once you've established the values. Of course, thanks for the question.
Okay, are there now any real last questions? Okay, I think that's going to sum it up. So like I said, thank you everyone for coming, and thank you, Allison.
Awesome. Thank you guys so much. Hope you all have a good rest of your night.